Welcome. In this video we'll be analyzing probabilities of independent events. Let's take a look at our first example. Example 1. You flip a third coin and then roll a third six-sided die. What is the probability that the coin lands heads up and the die shows a 3? We're going to be approaching this problem in two different ways. The first one is through a tree diagram. So what do? Since we know that first we need to flip a coin and it's a third coin, I'm going to list the outcomes here. So I can get heads or tails. And I know the probability of heads is 1/2 and the probability of tails is 1/2 as well. How do we know that? We know that because it's a fair coin. Now for the rolling of the die, let me list my outcomes here. I know I have 6 different outcomes. It's a 1, a 2, a 3, a 4, 5, or 6. Okay? That is possible if you get heads on the coin, but if you were to get tails, those are the same outcomes here. You could get 1 through 6 when it comes to the die. So we have 1, 2, 3, 4, 5, and 6. Now, the probability of each one of these outcomes occurring in the rolling of the die is a 6. Okay, so I can get a 1 with the 1/6 probability. I can get a 6 with the 1/6 probability, and so forth. Now, what we're interested in is the probability of getting heads and 3. So by looking at my tree diagram, I want heads and a 3. And all I'm going to do is to multiply the respective probabilities. So notice that will give us 1/2, the probability of H, and then a 6, the probability of my 3. So doing basic computations, this is 1 times 1, it's 1, and 2 times 6 is 12. Therefore, using your tree diagram, we get that the probability of getting heads up and a 3 will be 1/12. So that's based on the first approach. The second approach is to realize that these two events are independent. Okay, whatever happens on the coin flip doesn't affect what happens on your a rolling of the die, or vice versa. So whenever you have two independent events, we know that the probability of H intersection 3, okay, or H and 3, it's the same as the product if they are the product of the respective probabilities if they are independent. So here we have the product of H times the product, or the product of H and 3. In other words, we have the probability of H times the probability of 3. We know that the probability of H is 1/2 and the probability of a 3 it's a 6. And notice that's exactly what we have obtained based on our tree diagram, so that's still 1/12. Okay? So notice, based on this second approach, by using the rule of independence, we know that the probability of getting heads up and a 3, it's still a 12. So when you're solving this type of problems, you could use either method. Let's take a look at another example. Example 2. A bag contains 8 red marbles and 4 blue marbles. You randomly pick a marble and then return it to the bag before picking another marble. What is the probability that both the first and second marbles are red? Again, here we only have red marbles and blue marbles. So what I'm going to do, I'm going to list my outcomes. I either have red or blue. Now, the probability of getting red, notice you have 8 of them and you have 4 blue ones, so your sample size is 12, but 8 of them are red, so you have 8 12s probability of getting red. When it comes to blue, it will be the complement of that, so that's 4 12s. Obviously we can simplify this one. Okay, here you can say, oh, I'm going to divide by 4 and 4, so that's just 2 over 3, so that's 2/3, and then here again you can do 4 over 4, and that will give you 1/3. Now that's for the first marble that you're going to be selecting. However, since you're selecting a second one, but you're putting the originally selected one back into the container, we can list our outcomes as well. So we can get red or blue, or you can get red or blue. Now, since you put the red back in the container, you still have a 2/3 probability of getting a red and a 1/3 probability of getting a blue. Okay, again, since you put your marble back into the container here, the probability of getting a red one is still 2/3, and the probability of getting a blue one is still 1/3. Since we want both of them to be red, let's analyze the scenario that we want. We want a red for the first one and a red one for the second one. So we want the probability of red and red. Based on your tree diagram, all you have to do is multiply the probability. So you have 2/3 times 2/3. So 2 times 2 gives you 4, 3 times 3 gives you 9. So the probability that both of the marbles will be red, it's 4 nines. That's based on your tree diagram. However, you could have realized that since you're putting the marble back into the container, these two events are independent. So using the formula for independence, we know that the probability of R and R will just be the product of the probability. So you have probability of R times the probability of R. And we have already discussed before that the probability of R is just 2/3 times 2/3 in this case. So that's still 4 nines. Okay, so you still get the same answer. It's just that on the first scenario, or in the first method, we're actually using our tree diagram, and the second one we're actually using the formula, one of the formulas for independent events. Okay, so that concludes our video on probabilities of independent events. Thank you for watching, and good luck in your homework.